Hello everyone. In the previous lecture, we have seen the notion of equivalence relation, and we have also seen one of the first few examples of this notion. So let's try to quickly review what you have already learned. Yeah. So recall that if we have a set S, then a relation on a set S is a subset of S cross S. Okay, and if A comma B is a tuple inside S cross S that lies inside R, then you say that A is related to B by the relation R. Maybe there is something that I forgot to mention. This is something that you will get to see over and over again. In such a situation, sorry, in such a situation, sometime we write that A or B. Okay, A is related to B by this relation R. Okay, you have also, so don't be surprised with this notation. You have actually seen it. So as I have mentioned somewhere, I don't remember exactly where, that okay, maybe here, yeah. So we use these letters, sorry, or symbols, tilde or congruence and so on to, we use these notations very often uh, to denote a relation. So in that case we will be writing this tilde. We'll write tilde for R. So in that case, uh, this will become A tilde B. So you're already familiar with this A tilde B part, but I just wanted to tell you that sometimes we write A R B, where R is the relation, R is the given relation on the set S. Okay, and there are three conditions on a relation that we introduced, and later we saw that these conditions are very how to say uh, these conditions are very natural. There are several relations that you're already familiar with, and they seem to satisfy these properties, or maybe at least few of these three properties. Okay, so it's said to be reflexive if the quote unquote diagonal, so A comma A lies inside R for any A inside S, and it is said to be symmetric whenever you have a point AB inside R, you also have then B comma A lies inside R. And it is said to be transitive whenever tuples of the form A comma B and B comma C lie inside R, and if in such a situation it happens that A comma C also lies inside R, then it is said to be transitive. Okay, so note that whenever this hold, this has to hold. Okay, I'm not saying that for some ABC, uh, I'm not saying that for some ABC all these conditions will hold. No. So pick any three ABC, whichever you want. If you see that this is valid, then this has to be valid. Okay. Pick any three ABC. Okay. So if ABC are elements of S satisfying this condition, then this has to hold. Okay. Great. And then we saw this, I don't know, okay, this is usual less than relation. Then we saw this, probably this divisibility relation. Which one is the divisibility one? Yeah, this divisibility one, and then, yeah, this bit quote unquote unnatural one. And then we saw this, yeah, this even and odd, this parity relation or whatever. This is congruence modulo 2, as you will get to see here. So here we have this congruence modulo n relation, etc. So now we'll continue with this notion of equivalence relation further. Okay, so suppose we are given an equivalence relation on a set S. So recall that an equivalence relation is a relation on a set such that it is reflexive, symmetric, and transitive. It satisfies all these three conditions. Okay, so so please go through these notes and try to watch what I have said in the previous lecture, because I tried to explain a bit about this notion of relation. Because this definition may appear abstract, but in the previous recorded lecture, I tried to explain that. Oops, sorry. Oh, what happened? Sorry. I tried to explain that this is, how to say, this is a natural way to formulate the notion of a relation. Okay. This is not a that much surprising way if the notion of relation is formulated in this fashion. Okay, so moving on to today's material. So you start with an equivalence relation on a set S. Okay, and if you have an element X, then you collect all elements of S such that X is related to Y. Okay, so you may say that why we are looking at those Y such that X is related to Y. We could have also taken a look at we could have also taken a look at all those Y inside S such that y is related to X Yeah, I mean, I agree. And in that case, you may note that these two sets are equal, since tilde is tilde is an equivalence relation, or maybe since tilde is symmetric. Okay, great. Yeah, because if x is related to y, then y is related to x, and if y is related to x, then x is related to y. Okay, so this one is, I mean, so both the sets are contained inside each other, so these two sets are equal. So the equivalence class of an element x, of course under some equivalence relation, under some given equivalence relation, is the collection of all elements y to which x is okay, started with x, to which x is related. Okay, or yeah, or the other way around. So this is the one. So to which x is the collection of all the elements. Okay, yeah. So to which x is related. Okay, so this is the one. Anyway, so now let me recall some another notion that you might have seen at least in some form or the other. So if you are given a set S, okay, then by partition we mean something like this. Let me try to draw a picture. Yeah, so how do you kind of view a set? So if you have a set, it has a bunch of elements, right? So you just collect collect kind of a few of them here, and then collect some of them here. Then you do, I mean, collect them here. Okay, then this is a bad one to do. Or okay, yeah. So this looks good, right? So here you have a bunch of elements, here you have a bunch of elements, here you have a bunch of elements, and so on. Okay, and here again you have certain elements. So you may ask what happens if you also put a cross here or a line here. That is not good, because I mean, not good in the sense that that's not something we are interested in. So this part remains empty, right? So we will not do this. Oops. So we will not do this. Okay. Okay, great. So now let's come to the formal definition of the notion of partition. So if you are given a set S, then a partition of this set is a collection of subsets of S, and they have to be non-empty, all of them. Okay, so that's why I said that we do not do this. Okay, so not do this anyways. Maybe do not do this. This sounds a bit weird. Yeah, now this is grammatically correct. So do not do this kind of partitions. Okay, so do not introduce them. Great. So yeah, so if you have a collection of non-empty subsets of S such that any two distinct elements of C, they are disjoint. So have a look here. So if you pick at this collection of elements, or if you pick at this collection of elements, they are disjoint. Or if you pick this one, or if you pick this one, they are disjoint. So the point is that you decompose S into a bunch of pairwise disjoint subsets, okay, and C is formed by them. More precisely, a partition is a collection of non-empty subsets of S such that any two distinct elements of this set, they are disjoint, and the union of the elements of S has to be equal to S. Okay, this is a partition, right? So nothing can be left out. Anyway, so I just trying to motivate the definition. So a definition cannot be, I mean, cannot be proved. Okay, I can try to provide certain justification, but nothing beyond that. Anyway, so now we move on to an important result involving equivalence relations. So it says that if you have a set S and an equivalence relation tilde on this set, then if you pick two equivalence classes, then they're either equal or they're disjoint. Okay, so if you pick two elements x and y inside S and look at the equivalence classes Cx and Cy, then either they are equal or they are disjoint. Okay, so that is something nice, right? I mean, you have so for each element x you have a subset Cx, sorry, for each element x inside S you have a subset Cx of what? You have a subset Cx of this ambient set S, right? So if you pick two x and y, so for example, if you pick two x and y and it happens so that x is equal to y, then certainly Cx is equal to Cy, there is no doubt. Okay, I'm not saying that if x is not equal to y, then Cx intersection Cy is empty, let me write it down, because this is a crucial point. This is quite crucial, though elementary, but it may lead to some confusion. So are we are not saying that Cx intersection Cy equal to empty for two distinct xy inside S. Okay, so could you come up with a quick example where, where you know that this statement is valid, or at least where you know that this statement is false. Okay, in other words, this statement is valid. Yeah, again, one of the first examples of equivalence relation that we learn is this congruence modulo n, or this parity one. So if you look at consider tilde on Z defined by a tilde b if a minus b is even. Okay, then you certainly know that this statement is false, right? Because you may note that C1 equal to C3 equal to C5, this is equal to C minus 1 equal to C minus 3, and so on. So the equivalence classes of all the odd integers, they are the same, right? You can verify, okay? Because so what is C1? So you have to collect all the elements of S, which is Z in this context. So you have to collect all the integers such that maybe you just pick, suppose you are computing C of 1, okay? Suppose you are computing C of 1. Then you are collecting all the elements Y from Z such that 1 is related to Y. So we write that 1 is related to Y when 1 minus Y is even, right? That's same as saying that Y is odd. Okay, so this is precisely the condition, that 1 is equivalent to Y is equivalent to saying that Y is odd. Okay, so if you are computing C of 1, then C of 1 is the set of all odd integers. Set of there's not much point in writing. C1 is a set of all odd integers, and so one can show that C of any odd integer, be 3 or 5 or whatever, C of any odd integer is equal to the set of all odd integers. So in other words, this statement is false in general, and this statement makes sense, right? We are not saying that these the equivalence classes corresponding to distinct elements, they have to be disjoint. We are not saying that, okay? We are saying that if we pick two equivalence classes Cx and Cy corresponding to two elements, no, okay, so then they are either disjoint, and if they have a single element in common, at least one element in common, then they have to be equal. So this is a very strong statement. So try to go through the statement once, over and over again, to realize its worth. Okay. Anyway, so we need to prove that if we pick two equivalence classes, or equivalence classes corresponding to two elements of S, then they're either disjoint or they're equal. Okay, so you just pick two elements X and Y from this set S. If the sets Cx and Cy have no element in common, then we are done, right? Then you fall in the very first case, right? And so what we need to show is that, so when this condition doesn't hold, that is Cx and Cy have got at least one element in common. Okay, when Cx and Cy have got at least one element in common, then they have to be equal, right? So that's what we are going to do. So we are going to show that Cx and Cy are equal when they have a non-empty intersection. Okay, so of course we start with two equivalence classes and we assume that they are non-empty. So we assume that there is some element Z of S that lies inside both the sets Cx and Cy. Okay, so now I can write that X is equivalent to Z. I could have also written Z is equivalent to X. It doesn't really matter. Okay, so if we follow this definition very carefully, then if we pick some element Z from Cx, then you know that X has to be related to Z. Okay, and again, with the observation that, or with applying the information that tilde is symmetric, you get that same as saying Y is related to X. Okay, So let's just start from here. I mean, although you see that, if you want to go to y related to x from x related to y, you have to just apply this information once, and this is a kind of one step or just a maybe a half sentence long argument. Okay, great. So you know that. So again, I forgot. So yeah, so x has to be related to, yeah. So this one has to be related to the element. Yeah. So x has to be, so this x has to be related to the element z, and again this y has to be related to that element z. And now you use the fact that tilde is symmetric to obtain that z is related to x. And now you know that y is related to z. From here, you also know that z is related to y, and you use the transitivity of the relation tilde. Okay, so then we know that from these two that y is related to x. Okay, so now you pick an element s from Cx. Okay, then you know that x is related to s. You pick an element s from Cx, and then you know that x is related to s. Okay, now you use the information that y is related to x and x is related to s to get that, I mean, of course, combined with the transitivity, to get that y is related to s. Okay, it follows that the set Cy, the equivalence class of y, it has to contain this element s because y is related to s. So the Cy contains the element s. In other words, what we have done is that we have chosen one arbitrary element s from Cx, and we have proved that, and we have, oops, it is difficult to mark it. We have chosen an arbitrary element s from Cx, and we proved that Cy contains that element, right? So you have established that Cy contains any element of Cx. So the same as saying that Cx is a subset of Cy. And similarly, one can show that Cy is a subset of Cx. Okay. In other words, we have concluded that Cx and Cy are equal, and this proves the very first part. Okay. Now, this is the second part. This says that if you look at the equivalence classes, certainly the distinct equivalence classes, we can't repeat the same equivalence class over and over again. Why can't we repeat that? So let's go back to the notion of partition. The point is that, it has to be a collection of non-empty subsets where into distinct elements of C they are disjoint. Okay. And you know that if we pick two equivalence classes, then we can't kind of include the same equivalence class. Anyway, that won't even form a set. Anyway, so if you look at the distinct equivalence classes, then they form a partition of the set S. So why? So you need to have this kind of picture in mind. So one thing is that if you pick two equivalence classes, okay, then they have to be disjoint. That is one aspect, and the other one is that the union of all of them has to give us the full set. Okay, that is not difficult to see that the union of the equivalence classes is equal to the set S. Okay, because if you pick one element x from S, then x lies inside Cx. Why? By the reflexivity it's gone. So if you pick an element x from S, then you know that x belongs to Cx, since tilde is, so because then in that case, when we know that tilde is symmetric, if you use that information, then you know that x is related to x. So x lies inside Cx. Okay. So if you collect all the equivalence classes and take that union, you're certainly going to get all the elements of S. Okay. So there is no trouble with that. And then we need to show, which we have already done, that any two distinct equivalence classes, they are disjoint. Okay. Anyway, so we pick the set of all equivalence classes under tilde, and applying reflexivity, as I just mentioned, it follows that the equivalence class of any element of, oh yeah, there is another condition that one needs to show, which I forgot to highlight, although I have just added in the notes, that it has to be a collection of non-empty subsets. Okay, so we can't, as I said, we can't introduce some kind of a bar like this. Okay, great. Where is it? Yeah, so since applying the fact that this tilde is reflexive, we know that the equivalence class of any element of S is non-empty. Okay, so then C is a collection of non-empty subsets of the set S. Right, the first part is done, And now if we pick two distinct equivalence classes, then they're disjoint, right? Because you started with two distinct equivalence classes. If they are not disjoint, then they have to be equal, right? In that case, they won't be distinct. Okay, so the distinct equivalence classes, they are disjoint. Okay, and in other words, two distinct elements of C, they are disjoint. And now use the fact that this is reflexive, which he explained somewhere here using this marker. So to show to see that the union of all the elements of C is equal to S, and this proves the second part, right? Great. So the upshot is that any two distinct equivalence classes, they are disjoint, and if two equivalence classes, if they intersect, then they have to be equal. And from this it follows that, essentially from this, and using the fact that the tilde is reflexive twice, we see that the equivalence classes form a partition of the set S. Okay, so few more notations are to be introduced. Okay, so if you start with an equivalence relation tilde on S, then the set of all equivalence classes under tilde is denoted by S bar. Okay, this is a standard notation. Okay, so this S bar stands for the C that we have written here. Okay, yeah, and one can in fact show that the equivalence relation, there is something that I was about to say. I thought of saying it after a while, but maybe this is a good time to make that remark. Oops, just give me a moment. This has to be rotated. Yeah, so we are talking about equivalence classes. So it is important to note that if we change the equivalence relation, okay, on the set S, then the equivalence classes may change. Okay. Yeah, this is something that I will kind of state in a bit more generality. The example that I'm going to state. So still let me mention. So on Z, so there are several relations. So maybe this congruence mod n relation, or maybe just let me put 2, okay, just to indicate. So here's a relation, so where A is related to B if 2 divides A minus B. On Z, or maybe, okay, just let me write it here. On Z, one can also define another relation, this congruence modulo 3 relation. Or yeah, okay, so this is somewhat non-standard, though. You may say that we decided to write A congruent to B mod 2. Yeah, that is standard. So A congruent to B mod 3. So let's not follow these notations, but still, and I'll do so for a while. I'll take the liberty. Yeah, anyway, so the equivalence classes. So here the equivalence, how many equivalence classes are there? There's just 2, right? So one is the set of all even integers, 0, 2, minus 2, 4, minus 4, etc. So there are 2 equivalence classes, and the other one is what to write. Maybe 1, minus 1, 3, minus 3, 5, minus 5, so on. Okay. And for this, the equivalence classes are, there are 3. I'll write that in a moment, but what I was trying to highlight is that if you change the equivalence relation, okay, then the equivalence classes may very well change. Okay, so we talk about for example, in this sentence we have been talking about the equivalence classes, but it is implicit that we are talking about the equivalence classes related to this under this equivalence relation tilde. Okay, so we may talk about equivalence classes without without referring to an equivalence relation, but if we do so, in that case, it is it is implicit that we have one equivalence relation in mind. Okay, or maybe that the equivalence relation is it's clear from the context. Okay, yeah, so the equivalence classes in this case, they are again quite similar to what we have been doing. So 0, and then 3, minus 3, 6, minus 6, 9, minus 9, and then what's the next one? 12, minus 12, etc. Now this becomes difficult. So I need to kind of add 1 to all of them, so just let me do it. So it will be just 1, and then 3 plus 1 is 4. Okay, let me just do it in this fashion. 7 and then 10, or 10 and 3 13. So it has to be minus 2 and then minus 5 minus 8, or then minus 11 and so on. And there is another one, so which is 2 mm, mhm, is 2 and then 5 and then okay, I'm not making a mess. 2 and then 5 and then, oh, it's already there. So it's 2 5 8 11, and then this should be what, minus 4. Just give me a moment. I mean, this should be minus 4, but I'm just not able to. So just adding 2 to this. Where is minus 1? Yes, exactly, that was making that mess. It has to be minus 1. It has to be minus 1 and then, oops, minus 1 and then minus 4 and then minus 7, and then 11 plus 3 is how much? It's 14, and minus 7 minus 3 is minus 10, and so on. So these are all the equivalence classes under congruence modulo 3 relation. Okay, so one equivalence class is the set of all multiples of 3, and then the other equivalence class is 1 added to all the elements of, all the multiples of 3, and the other one is 2 added to all the multiples of 3. Okay, so sometime, just I'll put it in quotes, sometime we just write 3z for this, and then sometime we write 1 plus 3z for this set. Very often we do so, but since I haven't introduced this notation, so let me just not use them. Okay, anyway, so the equivalence classes, the set of all equivalence classes under an equivalence relation tilde is noted by s bar. Okay, sometime we may write s bar sub tilde, something like that, just to refer to the equivalence relation. Anyway, it turns out that the equivalence relation on a set S, they're in a one-to-one correspondence with the partitions of S. We have already seen that if you give me an equivalence relation, then the corresponding equivalence classes, they form a partition of the set S. One can also show that if you have a partition of a given set S, that corresponds to an equivalence relation, and one can define the correspondence in such a manner that the equivalence relations on a set S, they're in one-to-one correspondence with the partitions of S. Okay, so for example, here you have got this is one partition of Z, right? It has partition Z into the even integers and the odd integers, and that corresponds to this what do you call this congruence modulo 2 relation. Here you have partition Z into 3 subsets that corresponds to the congruence modulo 3 relation, etc. So one can show this. This is not too difficult to show, but let's move on. So if you look at the equivalence relation, I hope you can recall what was example 66. Let me remind you. So this is the congruence modulo 2 relation. So where two integers are related, if 2 divides the difference. Okay, yeah, so that was example 66. So I know this because I have done this. I have gone through this, so now I know what is example 66. Anyway, so there are two distinct equivalence classes as we have just discussed, and one of them is a set of all even integers, the other one is a set of all odd integers, etc. Anyway, so I have just discussed and I have just stated it as an example. Maybe I should set it as an exercise for you to prove it. Okay, or maybe this was already given. Okay, this was not given because the notion of equivalence class has been just introduced today. So anyway, maybe I should call it an exercise, whatever. So now if you look at so now we have the kind of a more general one. So this is the congruence modulo n relation. So there are n distinct equivalence classes. So here for the congruence modulo 3 relation, we stated that there are 3 equivalence classes, and we are saying that for congruence modulo n relation there are n distinct equivalence classes. Yeah, maybe this should be termed as an exercise instead of an example. Okay, great. So they are as follows. So for each integer between 1 up to n, you look at for each integer r between 1 up to n, you look at the collection of all integers k such that k minus r is divisible by n, or k is related to r, or r is related to k, or k is congruent to r mod n, just to follow the symbol that we have, just to use the designated symbol. So then one can show that this is an equivalence class. one knows that this is an equivalence class by the definition of equivalence class, and then one can show that this subset, they are all the equivalence classes. Okay, so now the set of all equivalence classes, we have been denoting that by this curly C, right? Okay, I mean, in the proof we denoted it by curly C, and we know that that has to be a partition, so we had curly C in mind. But oops, we just went too much ahead. So but for the congruence modulo n relation, maybe I should just write. So this is the congruence modulo n relation. So from this congruence, for this congruence modulo n relation, the set of all equivalence classes has to be denoted by this symbol, and this is read as Z mod nz. Okay, so don't call it Z by nz or Z divided by nz. I mean, I cannot say that is wrong, but I mean, we are not actually dividing anything. Okay, at least as of now. As of now, we are not dividing Z by nz. I do not know, as of now, we do not even know how to divide a group by a subset or by a subgroup, something like that. Anyway, so it is customary to, it's a standard practice to call it or to read it as Z mod nz. Okay. Sometime we also will also denote it by Z sub n, and we'll call it Zn. Okay. Yeah, I prefer this notation, but sometime I may end up using this notation too, in case I have to kind of write this over and over again. Okay, and the set of all equivalence classes under this relation is called the congruence classes modulo n. Okay, so what we have seen here, so these are the congruence classes modulo 2, and these are the congruence classes modulo 3. Okay, great. Then what? Yep. So now we'll show that this set of collection of equivalence, the set of all equivalence classes under the congruence modulo n relation on Z, so that has a natural group law. Okay. So let's try to define the group law. So we have to have a composition law that has to again be a function from G cross G to G, so which has to be from, in this case it has to be from Z mod nz cross Z mod nz to Z mod nz, because we want this set to be a group. Okay, so we define this as follows. So you take two equivalence classes C and D, of course under the equivalence relation, under the congruence modulo n relation. Then you define C star D to be the equivalence class of C plus D, where C and D are some elements from C and from this equivalence class C and this equivalence class D. Okay. Well, this sounds good, but there is a trouble. Why? If you just try to focus on the baby version of this, when n is equal to 2, then how do you define C star D? So for example, how do you add this one with this one, this equivalence class? Just give me a moment. Sorry, this is not a good one. So this is the equivalence class of, you can call it the equivalence class of 0 or 2, whatever. So I will just write 0. So the equivalence class of 0, and this is the equivalence class of 1. Okay. Yeah. So now we are trying to define a group law on Z mod 2Z. So we should be able to add C0 with C0 and C1 with C1. We should also be able to add C0 to C1. We should also be able to add C1 to C0. Okay. So let's try to add C0 with C1. Okay. So what does this recipe or this definition say? It says that, so if we pick C0 and C1, then it is defined to be the equivalence class of, okay, I didn't have any intention to write anything here. So this has to be the equivalence class of C sub C plus D. Okay. Now what is C and what is D? They are elements from this equivalence classes C and D. Yes. So where can I write? So for C equal to 0, D equal to 1. For C equal to 0 and D equal to 1, C sub C plus D becomes what is 0 plus 1 is 1, right? So it's good. So it is C1. But wait, uh, but wait, because we are choosing this element little c from c, okay? So instead of choosing 0 from c0 and choosing 1 from c1, we could have very well chosen what to say, maybe 2 from c0, and we could have chosen 3 from c1, okay? Then then the corresponding c sub c plus d will become c plus what, 2 plus 3 is 5, okay? I mean, so here, I mean, earlier we got c1 and now we are getting c5, right? Yeah, you might have observed, I mean, you might already be able to see that for n equal to 2, in other words, for the congruence modulo 2 relation on z, c1 is same as c5. That's true, but that might be just a mere coincidence, okay? And now we need to show that that is not a mere coincidence. This definition makes sense. There is no trouble, okay? So the trouble is that it was not guaranteed, or it was not immediate that c5 is equal to c1, okay? You need to show that c5 is c1. And more generally, if you pick some, maybe how to say, maybe some x from c, or maybe just let me stick to the earlier notation. If you pick c from c0 and d from c1, you have to show that c sub c plus d, is equal to c1. Or in other words, no matter what c and d that you choose from the set c and d, the equivalence class of c plus d will remain unchanged, okay? Because the point is that inside this equivalence class c, there could be more than one element, okay? In fact, there are, for this group, and inside d there are more than one elements, so there is no canonical choice for c and d, okay? So whatever c and d that you may choose from c plus d, from c and d respectively, you need to show that the equivalence class of c plus d remains unchanged, okay? No matter what c you choose from c, and no matter what d you choose from d. Great. So this is, so what I was explaining for a while, I've just written it down here. So to show that this composition law is well defined, in other words, we need to show that, very roughly speaking, we need to show that this composition law makes sense, okay? So the point is that an equivalence class under this congruence modulo n relation contains more than one element, okay? Thus the equivalence class of c plus d depends on the choice of the elements, choice of the elements c from c and d from d, okay? And we need to show that whatever c we choose from c and whatever d we choose from d, the equivalence class of c plus d has to remain unchanged. So let's do it. So we consider the congruence modulo n relation on z, and we pick two equivalence classes c and d under this, and then we need to show that the equivalence class of c plus d is same as the equivalence class of c prime plus d prime for c prime inside c and d prime inside d, okay? This is not at all difficult to do. So let's see. So if you pick, so we are given two elements c prime from c and d prime from d. We know that c is related to c prime under tilde. Well, why is that so? Yeah, so maybe I should add it as an exercise. It's again a one sentence long exercise. If we let me just try to explain it here, because this is the place where we had this equivalence relation. So if you pick two elements, if you pick two elements y1 and y2 from one equivalence class cx, what we know is that x is related to y1 and we know that x is related to y2, right? And now we can use the symmetry property, okay? That will tell you that y1 is related to x. Now you use the transitivity property. You know that y1 is related to x and that x is related to y2. So by transitivity you have that y1 is related to y2. So if you pick two elements from one equivalence class, then those two elements are related to each other under this equivalence relation, okay? Yeah. So you have chosen two elements c prime from c, then certainly c is related to c prime and similarly d is related to d prime. So you know that their difference is a multiple of n, and the difference of d prime is a multiple of n2, right? So it follows that if you look at the difference, difference of the sum, of the corresponding sums, then the difference is also a multiple of n. So we know that c plus d is related to c prime plus d prime, okay? So so you see that the equivalence classes of these two integers, they have a non-empty intersection, Why? Because because C plus D, it of course belongs to the equivalence class of C plus D, and since this is related to C prime plus this C prime plus D prime, this also belongs to the equivalence class of C prime plus D prime. So these two equivalence classes have at least one element in common, okay? And by that theorem that we just proved a while ago, we know that if two equivalence classes, if they have a non-empty intersection, then they have to be equal, okay? You may say that this argument is quite easy or kind of at least straightforward, okay? But well, I mean, we needed this lemma in order to make sure that this definition makes sense, okay? Or you may say that kind of one obtains this lemma under certain, after doing certain manipulation. Yeah, that's true. I cannot disagree. But this was crucial, okay, to make sure that this, this has any meaning. This makes any sense, okay. Okay, great. So at least we are done with this definition that, with the definition of composition law that I've introduced. So this composition law makes sense. So actually in this case, we say that this composition law is well defined, okay. And so if we have two equivalence classes CA and CB, so CA star CB is C sub A plus B, right? So because from CA, we can of course pick that element A because A lies inside CA, and you can pick B from CB, and then and then you can write that CA star CB is C sub A plus B, right? That is from what? That is from the definition itself. And so before writing all that, I just wanted to make sure that the composition law that we have just defined, that is well defined. Okay, I was wondering whether to move on or not. Let me discuss a bit. Or okay, so let's conclude here. Okay, so the lecture ends here. Okay, great. So we'll continue with this notion of equivalence classes, and more specifically with this congruence modulo n relation. With congruence modulo n relation with more detail. As you see that we just claimed a while ago that this set of all equivalence classes, set of all equivalence classes of the relation congruence mod n relation, equivalence classes under the congruence mod n relation on Z, that carries the natural group law. So we have defined the quote unquote the group law. We haven't yet shown that this is a group, so you're still not in a position to call it a group law. So you've defined a map from Z mod nz cross Z mod nz to Z mod nz that and you have also shown that that makes sense. And now the next task is to show that, at least let me highlight. Now the next task is to show that for this composition law that we have introduced in definition 80. So under that composition law, the set Z mod nz, it forms a group. Okay, let's try to at least do this, establish this theorem. Okay, so this is a set, that's fine, and this is non-empty, so things are well and good. And this composition law is defined as follows. Okay, so now if we have got three elements ABC from Z, you can show that the associativity holds. It follows from the associativity of the integers. Okay, so here we use associativity by the associativity of, or maybe integers, of integers Z comma plus. Okay, and so the associativity has been shown, and it's straightforward. And then we need to prove probably the fourth condition, quote unquote, quote unquote an identity element exists. I'm saying quote unquote an identity element exists. The reason is that we do not yet know that this is a group. Of course this theorem does state that this is a group, but we are in the process of proving that it is a group. So we cannot talk about the identity element. We can talk about the identity element when we have a group in hand. Okay, though we have a group in hand, but we haven't yet proved that this is a group. So we are in the process of proving that this is a group. Okay, but still there is no harm in kind of keeping in mind that the fourth condition is about the identity element. Okay, and it makes perfect sense to say that now we show the existence of identity element. This makes perfect sense only when this is considered as a slogan. This is imprecise, this is incorrect to say that we are going to show the existence of identity element. No, this is a slogan. Okay, you may also find these kind of statements in some of the references. That is probably very common or not too uncommon, I would say. but I mean, it has to be taken with a pinch of salt. That is just a slogan. So in the process of establishing that something is a group under certain given composition law, you cannot talk about identity element or inverses. Okay. So what you have to do is the following. So you have to show that there is something such that whatever element that you pick from the group or from the from that set and compose with that your favorite element, or using the composition law, you are going to get back the element that you started with, no matter what the order is, whether it is CA star C0 or C0 star CA. Okay. Anyway, so this follows because how to say, because because the equivalence class of C0, it contains 0, so when C of A plus 0 is by definition CA. Okay. Again, you may say that we are using the fact that 0 is the additive identity of the integers. Yeah, you are right in that case. And now we have to prove the existence of inverse. This statement is perfectly fine only as a slogan. Okay. So please be very careful. In the process of establishing that something is a group, you can't talk about inverses. Okay. What you have to show is that you pick one element CA and then you find something such that kind of when you such that when you combine them together using this composition law in whichever order that you may wish to, you get back the element. I mean, you get back your favorite element that you have worked on in the previous step, and that is again straightforward to do. So I mean, CA plus C of minus A is C0. Okay, and this shows that the set Z mod NZ forms a group under the composition law that we have defined in definition 80. Okay. Anyway, so note that this group Z mod NZ contains exactly n elements. Okay, and this this leads to the following question: that are there other groups containing exactly n elements? So are you familiar? If so, then write it down. Okay, and just few more notations and just remarks. The number of elements of a group is called the order of that group. Okay, if you have a group G, its order is denoted by this G within two vertical lines. Okay, the group of congruence classes modulo n that we have just studied, it is a group of order n. Okay, so if you look at the group of all integers, so how many elements does it have? What is the number of elements? It's infinite, right? So the group of integers is a group of infinite order. Okay, so for example, if you consider the group of, as another example, if you look at the group of 2 by 2 invertible matrices with real entries, that is a group of infinite order. Okay, yeah. And here is a remark that I didn't mention. So this was just to make our understanding more concrete. This is something that we have already discussed, I think, somewhere. Yeah, here, that for any A inside Z, the equivalence class of A under the congruence modulo n relation is precisely the set of all integers of the form A plus a multiple of n. Okay. Anyway, so please go through these statements and these results over and over again to make sure that you understand them really, really well, because these are one of the fundamental examples of groups that we will be dealing with. Okay, so kind of a large class of examples of groups come from Z mod n Z, and so please work on this question and other examples and exercise that we have been through during this lecture. Okay, let me conclude here.